cases of a UFO investigator.
Hello. I don't know if I can hear you guys or not. I don't think this computer has speakers. Anybody talking?
Hello?
Hello, there you are. It does have speakers. Okay. Well, guess we'll give this a whirl. Let's see. So this is a new computer for work. That's a Windows, so I can run some different programs. I don't know it very well. I just got it yesterday because I can't run a lot of these software programs without a Windows computer, and I've tried Boot Camp, and it just doesn't ever really work right. So this is a great solution. Hopefully it allows us to do a little bit more virtually. And if you haven't noticed, this is a software that allows you to look around as if we're out there at a wind site. So, here we are out at some random wind site, and you kind of see what the landscape would be like. And here we are at the bottom of what would be a GE 1.5 wind turbine, 1.5 megawatt wind turbine. You guys still hear me okay? Is everything working?
Yep.
Very good. Very good. Okay. All right. So when you get a chance, some of you have seen this software before, but some of you haven't. And I use this software to take us on tours inside this wind turbine as we're learning. And I think it really, really helps you guys get a better idea of what I'm talking about, where it is, what it does. And here we are looking up. All right. Does anybody have any questions? When you're at this point here, I want to back up. I'm just going to ask you guys as we go, what do you want to know about? What do you want to see as we climb this thing today? Is there anything in particular you notice?
There was vents on like the door there. Thought
Yeah.
that was kind of weird.
Yeah. All right. So we can go back up there. Yeah. Airflow.
Yeah.
So those are filters basically on the door. And that was very perceptive. I don't think I've ever had anybody ever notice those before. Good job. And I've been doing this 10 years. So we talk about filters in the turbine, but those right there are just basic airflow filters, keeping air clean and fresh inside your wind turbine. All right, so let's go back. What else do we notice at the bottom before we go inside?
Is that the PLC on the left?
This here, PLC, is that what you're saying?
Yeah, is it?
No, it will be in a box that looks like this. That's actually inside. This is a transformer. And we can take a closer look at that. So, I'm not sure. I know I can zoom in. I don't know how to do it on this computer. Whatever. So if we come here and we open this up, that box up, that's what it looks like on the inside. So those two doors are open now. What do you think you guys are seeing there? So this is where we're taking all that stuff I'm kind of yakking at you about for class after class or whatever. But now we're out in it. Try to imagine I wasn't there with you. You're working out in the field and everything is on you now. And of course, you can ask people questions about how things are, but you want to know what it is, right? You don't want to stand there asking people. So right now, this is when we ask, so we don't have to do it later. And it also really makes a big difference when you're working in the field and you're working next to someone who's experienced, and you're asking questions about stuff that shows how little you really understand about some of these things. You don't want that. You want to come out of school looking like you know what you're doing, and that's going to impress people to the point that they will continue to show you more and more and include you in things instead of exclude you, because you just don't understand. And so they don't have a lot of time to teach you this stuff in the field. You can get some stuff taught, but oftentimes you got a job to do, and you might be watching a person put stuff together. You kind of learn what they're doing, but you still don't know what you're doing. Just because you can bolt those cables on, does that mean you know what you're doing or anything about what you're doing? So a lot of jobs, a lot of people who are hired as wind techs, they're really just kind of an apprentice helper. They're never going to rise up the chain, and they don't realize that necessarily, unless they work at it. So what do you guys think you see there?
Those 4 cables on the right with the weird plugins that say X over them. Not sure what they are. They look interesting.
Good. You notice several things. X is one thing. Does anybody know? Does the X stand for a low voltage or a high voltage? Give me your best guess.
High voltage.
I heard a big ramble. Okay, so I'll just tell you. Low. Because the high side is labeled with an H, which you can't see, so that wasn't fair, right? But that tells you something right there, though. When you see the X, you're knowing you're on the low voltage side of the transformer. And if you see an H, like an H1 and H2 and H3, you're on the high side of the transformer. Let's talk about what those voltages might be. So let me help you out a little bit so you can get your bearings. So those cables that we see on the right, you see that they're going down. They're going down into the ground. Okay, so I'm going to back out of this. I'm going to grab our little screen here. Those cables are right here inside the box. They go under the ground in here, and then they come into the side of this concrete through a PVC. We do all this when we're still building the foundation. When we put this foundation in, we dig a big hole, and then we're going to pour the concrete that this turbine is going to stand on. We put a pipe in the center of that before we pour the concrete, and it's sticking out over here out of the ground. Then what we do is dig that out and put a transformer in there and pour a pad around it. But now we have a pathway underground between the wind turbine and its transformer. And that transformer is going to take that voltage from the turbine in 90% of the cases, I'd say, because there are different kinds of turbines that work on high voltage. But in most cases, you're going to take that and step it up. So this turbine is bringing in 575 volts into this transformer. Now, this is just the turbine transformer. This isn't a substation. This isn't a big, where they're actually, for all these wind turbines that are on this property, there's actually a station of transformers where they all meet. And that's what we call a substation. And they all go there before they go out on the grid. So this is usually the first step where we step up the voltage once. And then that transformer on this side, so I'll go ahead and open it back up. On this side are the high voltage cables. And you can notice those high voltage cables because of this special shroud you see. This is a high pot connection. You know, this is something you know I wanted to have in class so you learn how to do this. But man, each one of these kits costs almost as much as you going to school. You know, so it's not worth it. So, you know, you'll be out in the field and hopefully you'll be around somebody who knows how to do it. If they don't, they come with an instruction packlet and you should be confident enough that you can do it. But, you know, it's this thing that slips over it and then you heat it up and it seals tight around it and protects the cable. And so, you know, you're dealing with high voltage. High voltage has the potential to arc. Remember how we talked about, you know, arc flashes and arc blasts? When we increase the voltage starts to create such a potential difference that it is capable of jumping between those cables. So we have to do things like seal up the end of them, basically, so they're insulated from each other. And that's what you're looking at there. So those cables go back into the ground, and then they go out across the cornfield one direction. They follow the road, is what they do. And they head their way back to the substation. So it's okay if you're wrong. I don't expect anybody to know this, but can anybody guess roughly what the voltage would be, what this transformer is doing? It's taking 575 volts from the wind turbine and stepping it up to another voltage. What do you think that voltage is? Who wants to win the prize? Who can get the closest to the jelly bean contest, right?
12,000.
12,000? It's a good guess, but that's not it, and it's too low. Anybody else?
40,000.
Closer, but too high. So they're good. You guys you're in a decent, intelligent range there, I think. So this transformer takes 575 volts and steps it up to 34,500. And you'll see generally they kind of go, transformers go like from 480 volts to like 12,470 volts. Then you'll see ones that they do 13.8, and you'll see ones that do 34.5. You know, they have ones that do all kinds of different voltages, but you'll start to see there's like 4 or 5. So 34.5 is a very common one. 13.8 is a very common one. You know, and from there they go to the grid, and they get stepped up to whatever the grid is that they're closest to. So if you remember, we looked at the grid, how they positioned the wind farms close to the grid. Those grid lines could be 65,000. They could also be 765,000 volts. You know, it just depends on what they are. So the substation's taking all these wind turbines voltages and paralleling them together and running them through some transformers there, some larger transformers, and stepping it up to who knows what. and it's out on the grid. Okay. What do you guys think these colors represent?
The phases.
The phases? Correct. So you got brown representing phase A or line 1, orange representing phase 2, and yellow representing phase 3. But why brown, orange, yellow? Why not another color? Why not blue, purple, and pink?
Because they're easy to differentiate between.
Say that again.
Because they're easy to differentiate between.
Well, think standardization. We phase our cables black, red, blue sometimes too. Some of you guys have been in class long enough, you should know. Those of you who have been in school for a while, why we have brown, orange, yellow instead of maybe black, red, blue. Well,
People who are colorblind, maybe?
no. Colorblind is an issue. Yeah, with electricians, you shouldn't be colorblind and do electricity, but you can. It simply means, anybody else have a guess?
I was just going to guess that it might be because they'll be easier to distinguish if they fade.
Well, that's why we phase them. Yeah, we phase them all different colors, and so we know which one's A, B, and C. But the reason why the color is brown, orange, yellow is because it represents voltages over 480 volts. So if you open up any box and you see brown, orange, yellow, that tells you right away that you're dealing with high voltage. If we're dealing with voltages that are 480 volts or lower, you'll see black, red, blue instead of brown, orange, yellow. Regular couple of things. You can, not really. Thank you. Okay. Anyway, I think that's about it in the transformer, you know. I mean, there's a ground wire in there that we saw. That was that bare copper. Okay, and then these down here are important. We don't have to focus on them, but they're the anchors that hold the turbine down. And, you know, one of your jobs is to annually check the torque on all these and make sure they're staying tight. Okay. If you're the kind of person that doesn't like working with electricity, there's lots of different types of jobs out there mechanically, and they're important, you know, that you can do. But typically, you're going to get to do it all, which is really probably what you want. You get a variety.
Inside that transformer box, what was the little fan blade that's inside there?
This right here? Oh,
Yeah.
I didn't click on that one. I think it's just a little graphic on how transformers work.
Oh.
You know, and so we cover that in several classes. But you know, this is the windings. They're separated. The cables are hooked up to them, and you know they're breaching. Their voltage is magnetically inducing into each one. So it's showing you, you know, the primary windings coming in, and then you've got a magnetic field that goes into the other winding. And so stepping it up or stepping it down really has to do with one winding is bigger than the other. And so you can't, right there, 10 times more windings. So you could get 10 times the voltage in the other winding. Oh, man, it knows what it's talking about, right? or you could go in the opposite direction. I think that's all I had on there, it looks like. Any other questions on this? IDT 125, we talk a lot about transformers and some of the details on them, make you a little more comfortable working around them. What matters a lot is just the connections, good connections. There's not much to them. You're connecting to them, but are your cables crimped properly? Most of the time, the stuff's already done. If you're just coming to a farm that's already there, if you're working with one that's being built, you're gonna, whoever's doing these crimps, you know, if you're in a position of responsibility, you're going to be checking those things to make sure all this stuff is solid, insulated, phased, torqued. All these bolts are torqued to the right torque, that kind of thing. All right. That right there's a light, if you want to know. That's just a light. And a lot of times in the winter, you get ice on the side of the turbines and they slide down and they just take the light right on off. So, not a big deal. Let's go inside. Here we are. These are, I'd say, early 2000s GE wind turbines. And so they have the ability to power or create 1,500, let me back up, 1,500,000 watts an hour. So each one of these is powering a house an hour, roughly. They don't run at full speed all the time, though, so they're usually about 50% in there. So you're usually producing about 700,000 watts an hour, which is still enough to power most homes. But they can go all the way to 1.5. All right, let me back out of here first before we start looking at a bunch of crazy stuff. So in here, there we go. We're looking around. I'll try not to make you sick, but these boxes right here in front of us are electrical boxes, and they're on a raised platform, so we can bring cabling in underneath them. This version of turbine has a odd deck up here. Usually there's no deck there, or they're a little higher up. So here we are looking from the bottom up, and if you've never looked inside a turbine or wondered what it would be like to climb them, there you go. You know, the decks are usually, you know, around 50 feet apart, something like that. 50 to 80, depending on how many they are. They're usually maybe 3 to 5 in a turbine. And there's your ladder. And the thing about the ladder is you're not climbing with your back facing the middle of the turbine. When you climb, your back is actually against the wall of the turbine. And so you can literally climb and stop, let go of the ladder, and lean your back against the wall with your feet on the rungs and not fall down the ladder. And you also are connected with your safety lines. Does anybody have any questions on that view that you have right there? There is a lot going on, I know. And there is power cables running down the side of this turbine and communication cables. We'll take a look at those as we go on up. But before we do that, we can see right down below us here is the deck, and you can remove those plates and crawl down underneath there, which is, yeah, I don't know. These are a little more shallow. So it's not a comfortable experience. You're not always crawling down in there, but the reason why you do that is because some of these cables are coming in under the floor and going in the bottom of these boxes. All right, so here we are looking out our door. There you can see your filters there, not much to them. And here we see another box. This right here is the chain hoist. So there's a control module down there allowing you to drop that down lower, where you can hook a bag and haul that all the way up the turbine so you don't have to carry all your tools. Okay. And then this is your computer terminal. It's just usually an old computer. Heck, the ones I see still have like CRT monitors in them half the time. But, you know, it's just trying to show you your SCADA system right there. And you can see that also in your office or wherever you're connected to the SCADA system with your network. And you can tell if a turbine is on or off. You can actually turn it on or off. We've had guys in the classroom that connected to the turbine, and they would turn it on and off for us, which was kind of neat to see that you could do that. And pitch the blades or do whatever you want, really. And you have your computer right here, so you can just connect to it. And these controls here are your manual controls. Remember how we talked about having manual control? So you have different switches there that you can switch the blades to manual, switch the yaw to manual, switch some of the different systems, and then you just yaw in one direction or another, like we said, to determine what is going on. So we'll click on this, and you'll see real quick it gets complicated. So when you open this up, behind there is several devices, and I know what most of that stuff is, and you'll learn what most of that is when you get into the 211 class, and you have a that's right there is your power supply. You remember how we talked about a PLC system has like 4 basic parts. Power supply, there's one. And then right here is going to be your processor unit. And then right here we see all these little lights. Those are going to be your input and output modules. Okay, and then all the wiring runs in here, and it connects into some sensors that are at the bottom of the tower. And those sensors at the bottom of the tower are, who knows, you know, they're all over, little different things. Measuring voltage, for example. Like this is an MFRU sensor, and that's telling you what the current and the voltage are through current transformers. These little clamps that are the same thing that's on your meter, clamp on meter. They clamp around the power cables, and they're telling that device what the voltage, frequency, a lot of information. This is a really smart device, and that device is also connected back into the system, and it's able to give a readout here. So that's where you're seeing like the voltages and stuff here on your computer. It's because this thing is measuring it. And so you have also these relays here, and these are either 24 volt or 120 volt. So this one you can't probably see, but it's orange. So it's a different voltage than these that are blue, but they're just a little box that you bring the wires in the top in and the wires in the bottom out, and they're a switch. So what happens is this PLC has solved some kind of logic, and then it sends its output through one of these relays that closes, and then that's going to turn something on. Okay. And then down here on the bottom of it, all this stuff, which looks complicated, all it really is are breakers, breakers for these switches. So you've got some of them, like these red ones here, are a little different in nature. Those are surge protector type breakers. And then these are breakers that have the ability to do maybe time delay on them, turning them on or off, and somewhat adjustable. And then you have some weird things in here, like this thing right here is a sinus filter. What a sinus filter does is just suppressing voltage surges so it doesn't destroy any of your sensitive equipment. And down in the bottom is some battery UPS systems. And this is your Intron, which it's your router. It's your router for your whole wind turbine, and then it connects to the internet that way. Any questions on that?
This doesn't have to do with the panel, but I saw there's like a little key or something on the hook by the computer. I was wondering what that was for.
Yep, that key is the key to open this lock right here. See it?
Gotcha.
And all these doors use pretty much the same. You can use a tool to open them, but you tear them up. So they just leave the key there, and you grab it and put it back. So everybody always has a key. You can lock them more if you want, but what else? There's a lot of electronics in there, I know. But hopefully after everything we talked about today, that kind of makes sense on what's going on more than maybe it did before.
John, could you summarize again all of the variables that you'll usually be able to see there?
Yeah, so something important to know, everything in the turbine is not in this one area. Well, we do call this a control area. So these other cabinets don't look like this. There's other stuff in them. But what we call this is the master PLC. Now, once we climb to the top, we go, so we call this down at the bottom the DTA. So this is the DTA assembly, or the down tower assembly. When we go to the top, we have an area where we have the top box. Inside the top box, which is just a box like this with, I don't think it has the computer screen on it, but everything else. I don't think it has a keyboard either, but up there it looks just like this, but there's a lot more up there, and that's the slave. So what happens is, whether it's to the top of the turbine and the bottom of the turbine, we have all those variables, all those sensors, and that could be anything from wind speed to the generator voltage, the generator speed on the high shaft, the low shaft, the direction of the wind, the blade pitch, the direction of the yaw, the vibration of the sensors, the temperature of the bearings, the temperature of the generator, the temperature of the gearbox, the temperature of the oil, on and on I can go. There are just tons of them. And so all those sensors are running into either it depends where they're at. If at the top, they're running into the slave PLC up there. We call it the slave because it reports down to the master. surface. This is the master. And so the master is really, the slave and the master are somewhat of a clone of themselves, but the master acts like it's the main guru. So everything gets reported to the master, and the information that it uses from the variables that you have, it takes all that stuff and solves the logic. Does that mean, you know, turn the turbine this way, that way, speed it up, slow it down, turn on the brakes, whatever situation you're in? And that's when we start to see the output sending out signals to these relays to close and start doing whatever it is that we want it to do. Turn out of the wind. So upstairs, all those relays that are controlling the blade pitch, they're upstairs. So that slave PLC is going to be up there doing that, handling its business, just letting the master know what it's doing. And then down here, we'll have some other things, some motors and pumps and some systems that we'll look at that this side is controlling. That answer your question?
Yeah. And so I imagine for every sensor that you have collecting data, you'll have sort of a like acceptable range.
Yeah, we'll call that a threshold. Yeah.
And then once it reaches a threshold, then it sends the signal for some action to take place.
Yeah, so that threshold could be, if, how it would be wrote in a programming language, they would write, if the voltage is above 600 volts, do this, right? And then it would also say, but only if this and this and this is also happening at the same time. So it can get really complex, right? But if one of those systems goes down, you can see how it can affect the whole turbine from operating properly. And so it's very important that you're able to find the root cause, because there could be a lot of symptoms caused by a bad sensor, causing a lot of sensors not to be able to function. And that's what makes it kind of, you know, fun. A lot of detective work, trying to figure it out. Any other questions? Okay. Let's see here. Check my power on the computer. We're still doing good. Oh, it's going fast though. Let's see if I can't plug it in. And it is 11:30. Okay, we got time. All right. So let's look at some different cabinets now. This one right here, which is right next to the PLC. We open that one up, and we're seeing some stuff in there. Now, the pictures are blurred out for proprietary reasons, so you can't see the manufacturer or anything like that. But, you know, you can see what's going on. And I do actually have the prints for, I believe anyway, for all this stuff here. And so inside there, we're really just seeing fuses on some of the systems and breakers. And down here is a transformer. I believe this is running like the lights in the turbine, and it's running, you know, outlets and things like that.
So close.
It's more of a panel, power panel. And so they're just reiterating different ways of circuit breaker protection. So, all right. So any one of these things could be a problem too. You know, you got a fuse that blows. You're going to have to check the continuity of a fuse or even a breaker, whether or not it's working or not. I just replaced one on my hot tub, you know, because it wouldn't trip right. And I'm not sure what this is. I can't remember. Honestly, it looks like a variable frequency drive, but I don't think it is. But down here, this is a transformer that is what we do is we take some of that voltage and turn it into like 120, so we can run lights and outlets. So it's taking that high voltage that the turbine already has from the grid and just stepping it down to 120 or 240 or whatever it is that you need. All right, any questions on that? Okay. And when we open this one up, that one is, I think, a little more interesting. What do you guys think that is?
Looks like a big breaker box of some sort.
It is. And in our classroom, next time you go back to campus, in the classroom, I think we have this right here, so you can get a closer look at it. And yeah, this is just a ginormous breaker. That's basically what it is. So the power cables coming from the generator are actually coming in the back side of this panel. They come down the tower and go behind these panels in a little tray that we can't see. And then they come in the back. And this is what we call the line side. You know, where we talked about the line and load side. So they're coming in the top. And then these are just very large, arc-protected GFCI high-grade, high-voltage connection points. It's a bus system. It's metal with some protective barriers to prevent arcing. Okay, and it's also reporting back to this breaker right here, which this breaker right here has several connection points on it, small wires, and you know, you can see like a bundle of wires back here, and they're connected up here, and there's sensors here telling it, you know, what's going on as the voltage is coming in. And it also allows you right there to, that's where they open. So if I want to turn this entire wind turbine off, I don't want it connected to the grid, this is where you're going to do it, guys. You're going to pull the big master switch and lock it out. That'll be the first point of isolation if you're going to be working on this. Okay. And inside here are also the current transformers that you can't see very well, but this is like a little square with a hole in the middle where the cable is running through. So you got 1, 2, 3. And then you've got these wires. Hold on. You got these wires that are connected up to that relay. Okay, so you're like, what are you talking about? So, you know, we're going back into this box all the way over here. We talked about this MFR relay that's measuring the voltage on the turbine and the current through current transformers. That's them right there. So they're connected around the wires here on the top and on the bottom. And they're able to measure the voltage and they send that signal out. And so you can see these wires are going to weave and wrap through each one of these boxes through the different channels It's very well organized, even though it looks like a lot of different stuff. But once you start getting familiar with everything, you know what you're looking at and where things go. Any other questions? Okay, so we've looked at this side of the DTA. What's on the other side of the DTA? So there's really nothing above us. So we'll go ahead and open up this box. What's that look like?
It's a fan to cool something, or I don't know.
Yep, it's fan, and it's your coolant system. So depending on the kind of turbine it is, they'll have like air conditioner. It's a radiated system. So you're like, oh, okay, but that means you need to know how to work on this stuff, right? So you got electric motor, you've got some lines running to a compressor that's creating, you got coolant and a compressor, and it's trying to take all the heat basically out of the cabinet and blow it out. Okay. Go ahead and look in here. Oh, what's that?
Capacitor bank. Maybe.
Capacitor bank. Why do we have a capacitor bank?
I don't know. It looks like capacitors on the top there.
Looks like a what?
It looks like capacitors on the top of the blue
Right,
cylinders.
Yeah. What my question to you guys is, why do you think those are capacitors? Why do you think we have capacitors in there? Those are big capacitors, by the way. Like bigger than a can of pop.
Help smooth out the voltages or the voltages when the turbine slows down or speeds up a little bit.
Kind of. I'd say you're right. But it is power conditioning, and it's not so much smoothing the voltages. A lot of that's done right here. This right here is your power converter system. This is where it's taking some of that power and changing it into 60 hertz AC. Okay. These right here are examples of gates. We talked about gates on a circuit board. These are gates. So you have a base. The base is telling that gate when to open or close. And so that's the transistor right here. So when you reach a certain threshold here, anyway, this is just circuit board stuff, how things work on a circuit board. But this right here, this board is our inverter, our rectifier, our converter. It's taking that power that's from the grid. I'm sorry. Well, it is using the grid. It's looking at the grid, and it's taking the power from the wind turbine that's being created, and it's going to be regulated to a point, but it's going to be wild at the same time because wind speeds change. And So it takes that power and cleans it up into an AC 60 hertz sine wave. So if you remember the analogy of, you know, having a creek or a creek run into a river, you know, they need to be synced up. They need to be flowing at the same speed. And so it's getting the voltages in sync with the voltages on the grid and the current. Now that's where things become interesting, and we'll come back to it over and over again. And some of you guys will just remember, you know, when we're talking about AC and DC power, there is a big difference, and more so in the idea that AC power will get out of sync with itself. So you have voltages and current waveforms that are supposed to be going up and down in a cycle, 60 hertz a second. But because in an AC circuit, we have, and if you guys remember from basic electricity, if you've had that, we have inductive reactance and capacitive reactance. We have the things called VARs, volt amp reactance. And that volt amp reactance is what makes the voltage and the current waveform get out of sync, or in other words, inductive reactance. And we put a capacitor in that circuit, because what happens is the voltage in an inductive reactive circuit, the voltage is leading the current. It just does when you have an inductor. And the inductor that we have is the generator. And an inductor is a coil of wire that's working on the principles of electromagnetic force. And we get issues that come with that. Even more so when it's wild, being powered by the wind. And so we have dirty power is what we have. And so the voltage is going to lead the current, usually by about 90 degrees in the waveform. And the easiest way to understand that is we put a capacitor on that circuit, and a capacitor does not allow voltage to pass through. However, the current does. The current stays equal, stays the same, that type of principle, okay? But the voltage actually has to charge the capacitor up first. And so the best way to think of it is when we get into that situation, we have dirty power, and we want to clean it up and get it synced up, the amp and the voltage sine wave synced up. So the voltage tries to lead the current waveform, but it hits that capacitor and it slows it down. And we know how much to slow it down by a calculation, the inductive reactance calculation we actually learn in basic electricity. You know, because we fix inductive reactance by adding capacitance. We fix capacitive reactance, which is the opposite, by adding inductors. So once we put these capacitors in the circuit, the voltage hits the capacitor and it has to slow down and charge. This gives the current waveform a chance to catch up. And now they're in sync. Then they also go through different processes of rectification on this board. where we're trying to do different things with the power. That's a whole nother can of worms where we're using magic tricks to make the generator run in broader ranges, yet still creating 60 hertz of power that we can put back out on the grid. It's pretty amazing, really. And so we have this is what's really going on in here. And you can see you got 2 fans in here. These 2 fans are pulling the heat out of the system. And then you also see you got these hoses here. These hoses are the liquid cooled lines, I believe, anyway. Some of them are just air cooled, but this is the antifreeze system that's trying to keep everything cool. Any questions on this? A lot of crazy stuff going on there, huh? What do you guys think? How does this make you feel now that you're starting to see and peel away the onion layers of a wind turbine?
Kind of feels like I'm in a boat or something.
In a boat? You said a boat?
Yeah.
Oh, really? Why is that?
Just the circular door and, the all metal and industrial kind of thing.
Right. Well, that's what's at the bottom of the tower. You guys ready to go up? So in order to go up, all we have to do is just click this button here.
What was in the last cabinet?
Oh, we didn't do that, did we? This one, right? Yeah. Very good. Now, let me grab my power cord while I have a chance here. Let's take a look at that. What do you think it is?
Are they fuses for the phases?
Sorry, I couldn't hear you. Say it again.
It's something with the phases. Maybe are they fuses?
I can see how it looks like fuses. We just looked at one, a big one, when we first started this. Transformer. That's what a transformer looks like when you take the metal box off of it. And that's not a very big one. This box is kind of complicated. I don't even understand some of the stuff that's going on here very well. This is just not telling us anything. I don't think they even know what's going on in there. They just put some fancy picture there. This is part of the power conditioning process. This is a line reactor. And, I mean, again, it's going back to what you were saying, Josh, smoothing the voltage out. So I have a whole booklet on how this whole thing works, and we try to pick it apart. But there's a lot here that is, I don't know, not very interesting. But it's basically a transformer that's helping in the process of power conditioning. Okay, we want to keep going before we get behind. So I got to go grab that power cord. I'll be back in about 30 seconds. Just kind of look at this and what do you see kind of thing. Okay, I'm back. Any ideas? You got one box right there. That box is, I honestly have never seen one in the field before, but what I understand is that's a field or a lighting box, a control lighting box. So that's usually in the bottom of the tower. All right, let's take a look around. Just something to note, you can see right here, we'll eventually talk about safety, but you can see right there's a clip-on point. Pay attention to what those are so you're working safely. You have a hatch here, climb up, stand on this deck, and if you're ready, close the deck, close the hatch. If you're ready to go up the tower, and what you do is your harness clips onto this cable. So you're always connected. So if you fall, it'll lock right here. And so when you climb, you just start climbing with your back against the wall. Up you go. And it's just a big ladder. And as you climb, this thing is going to stay attached. There's definitely other things we could talk about there, but that's climbing in a nutshell. And coming down here, you can see the different cables running down the wall. So click on some of these things here. That's showing you, bird's eye view of what's inside them. Big long cable. Usually they're like a 250 kc mil size cable, which is about the size of a quarter. Oh man, see right there, that was weird. See, they have these phased here. Black, red, blue is what they are. They got a white too, which means they got a neutral. This is a weird system. I don't know about that. We look in our lighting box. That's basically it. What's interesting is you'll be working on a GE 1.5 from 2005, and then you'll go work on a GE 1.5 from 2008, and this box is just completely gone. Or something like this. You go like, that looks important. Nope, it's just been replaced with something else. It's kind of baffling all the different ways that this stuff can be engineered and even improved upon or made worse. One of the bad engineering decisions I've seen over the years is they had a deck like this, but it was up much higher, maybe about up here, a full deck. And then up there they had all these connection points for these wires, and they had a couple boxes like this up there. And then the following year, they just took that deck out, but they left all the stuff up there. And I just was like, why did they do that for? Not realize you got to work in those boxes? And their answer was, build a scaffolding. So things can be engineered better, but not always. They were trying to save money is all I can assume on steel, or they're in a transitional phase. I don't know, but a lot of head scratching there. All right, so we'll go up to the next deck. It should have just started spinning. Wrong way. This one's There it goes. All right, there we are. I wanted you to, it spins smoother if I don't do it, so you can take a look around. Not much there, is there? Oh. I don't know what that's doing. So I can't zoom on this computer for some reason, but my Mac has a different kind of trackpad. It's real nice because I can zoom right in and read, what that's saying on these walls. I just can't seem to do that with this one. Maybe if I hit Control P, doesn't look like it. Nope. All right, whatever. We don't care. So you have all these bolts here. These bolts have to be torqued down to a certain specification annually. So what we do, and you can kind of read this one. It says KJ 10%, 9/18/2008. That meant, I don't know, Kevin James was in there, and he torqued 10% of those bolts. So what you're doing, and you'll learn this over and over again, that you don't torque them one at a time, right, one right after another. You do it in a star pattern, and you only do 10%. And then if you do more than that, then, well, if one fails, I'm saying if one's loose, then you have to do them all. So, and these are the kind of jobs that people who don't know much about electricity or don't like electricity can find them doing. And also, that's also something that a lot of everybody does. So if you're a good troubleshooter, you should be pretty busy troubleshooting all the time. And then a lot of the new guys end up doing this kind of stuff in between. And then you work your way up into troubleshooting, and then somebody else takes over this role. Or you got somebody who's a mechanical person, and they just handle all mechanical, hydraulics, bearings, torque, metal, fatigue. There's a lot of interesting aspects to some of that stuff too. So, go in a little closer. That's what you're looking at. Somebody there with generally a hydraulic or an electric torque machine. We practice this in a class. We learn how it's done. It's pretty easy. These right here are bonding jumpers. They bond the two towers together because they're actually two separate pieces. And so they're just making sure you have a solid ground for lightning protection purposes. That's where the hoist comes up and down. And those are a continuation of all the cables. So you can see here, when we're talking about that one, what are you doing, computer? Doing something I don't want it to do. Okay. You have the light right here, you see, in the power cable. If you recall, we were looking at that one cabinet, and I said I don't think there's really anything in here except I believe that transformer is there for this lighting system and power system. So those are an example. Then you have phase A, phase B, phase C. So brown, orange, yellow cables coming down. These are the same ones that run out to that transformer. They go through a couple different connection points that we saw, like the circuit breaker. CB1 is what it's called. And then over here we see, usually you have maybe the ground wires bundled in here with the power cables for the lights. And over here you'll see some other power cables that do run top to bottom. I think they run at an odd voltage like 690 and 400 volts for some devices that need that voltage. But you also have your Ethernet cables that are connecting to your master and slave PLC in these clamps as they go up. You can see that deck's a little farther than the other one. Any questions before we head on up? All right. Now, this is generally the last deck in all turbines if they have it. Again, they're different. So the concepts are the same, just like a car, but they're different. The deck that we call this is called the saddle deck. The saddle deck is where we look at the drip loop usually. And it's the last deck below this deck, which is the very top. We call that the yaw deck. Saddle deck is generally the deck where you have all these cables, the generator cables that we saw when we split up. They come down in a big bundle and they go over what's called a saddle. And recall, we talked earlier in the lesson today about when we yaw, we don't want to rip those cables. We don't want the turbine to twist so much that it tears those cables up. So those cables have a little slack in them to allow us to turn that turbine maybe 3 times. And then there's a sensor up there. It's called a twist switch sensor that will trip. Or there's other sensors that do the same thing in a different kind of turbine, and it'll trip. But these GEs have a twist switch sensor, and they trip, and then the thing will reset itself and prevent the damage that we're talking about happening to these cables. You know, over time they start pulling on themselves. This used to be a really nice, clean. All the wires were straight, but you can see as time goes on, the tie wraps break off. They twist themselves apart. So other manufacturers will have like a different way to do it. They call them snowflakes, where all these wires stay kind of in clamps. The problem with that is, you know, a lot of times they're longer than this, and there isn't even a deck in the middle of the tower to work on them. And so sometimes you have to use an SRL and climb off the back of this ladder to reach it. You see how that's not very comfortable. But, you know, you can do different things to make that safe, and we'll learn what that is. Any questions? There's another picture of it. So this is a place where you want to pay attention to, because you can have a lot of rubbing with the wires here, chafing, that can damage the cables. Because these towers rock in the wind quite a bit, and you'll see these cables swinging all the time. All right, let's go on up to the yaw deck. So in the yaw deck, what we're looking at is all the different parts and pieces that really have to do with, one, the hoist right there in front of us. That's where the hoist is that drops the chain down the tower. And then we also have this right here being part of the yaw system. So this is what we call the slewing gear. And there's a bearing right here. And what you can't see up here on the floor are motors that connect to the other side of this gear that you can't see. And that's how it turns at the top. And oftentimes there's brakes here too. Not all of them have them. This one doesn't have a brake system here. It has a passive brake system. You can see these little pucks up here, and we'll learn what those are again. Right here is a greasing manifold that just spreads grease throughout this gear. And it's automated most of the time. You still got to check these connections. I've seen them hanging down. People put their feet on them and break them. So you want to watch those. And then, of course, there's grease that you got to pump in there. But again, you know, it doesn't mean that's what you're going to do all the time. That's just a task that some people will do. And you can see they've got a lot of torque marks on here. The different colors represent the different year or date where they ran this torque mark. And it's the torque mark you're looking at. So when you tighten this bolt down, if it moves, these will no longer line up. And when they no longer line up, this paint mark that someone puts on there that tells you that that bolt was loose or it's changed, expanded, fatigued. Generally, you just give it a little torque and it tightens up just a little bit and it's good. And then you would re-torque it. But if one failed, again, you'd have to do all of them in here. All right. Here we are at the top. I'll let that pan around so you can get a decent look. Nice thing about what we're doing here is we are recording this, so you can always go back and watch this over and over again. I know there's a lot of stuff to take in, but you know, I'm trying to do a little bit more detail here so you can go back and watch. Maybe pick up on some stuff I might have said that you missed. So what do you guys think? Do you want to work on that machine?
It's a lot bigger than I thought it'd be.
Good. That's what I want you to notice. What else do you notice? Just, you know, I can walk around and point things out to you, but I've seen this stuff a million times. It's always curious to me. You see things from a fresh perspective, maybe in stuff I forget to mention. Well, if we take a minute and look, you can see right here is some padding. What do you think that's for?
Sound. Or noise cancellation.
Correct. This has a name. We call that the low-speed shaft. That is connected directly to the rotor assembly. The blades in the hub are bolted on right here. So if we took all these bolts off, what do you think could happen?
Would the blades would fall off?
Yeah, they could literally fall off.
That would be decidedly not good.
Yeah, so making sure those are torqued right. I'm going to tell you a little story. So I went out on the blade once, well, many times, but this time, we were working on a new construction site. And when you do that, you've got people who aren't wind techs, really, working on some of this stuff. They may even be brand new apprentices. You never know. But I've been doing it for so long, it doesn't make sense to me that anybody would leave some of the nuts off of this. But I climbed out in that, and I came out, and there were several of these nuts missing off of this thing. And I threw a fit. You should never allow people to get up in a turbine in that situation. I don't even understand why they thought that was okay. Unbelievable. So, watch out. You learn, from that day on, when I got ready to go out in the hub, I would always walk over there and look. That's kind of a common sense thing. You wouldn't think you wouldn't have to check, but yeah, you do.
It seems like those get loosened up quite a bit.
Tightened and checked? Yeah.
Yeah. Like they move.
Yep. Oh, yeah. Well, maybe. I mean, the different colors, that's just months.
Lines just, it looks like they've moved.
Well, you probably are seeing some of them that have, yeah. So I agree. And unless we can zoom in on there, well, what's this picture do? Let's see. Nothing. Okay. That's the same thing, a different kind of turbine. But yeah, you're right, and we can't really tell what's going on here exactly. But yeah, they will move, and they do move, and you've got to make different marks. But also, the different colors represent they've just been checked a lot, and so you're going to have to put a paint mark on them whether or not they move. They always get a paint mark.
Or I guess, did those get checked more often than the other ones or whatever? Yeah. Probably.
I would say there definitely you have a looks like twice as much maybe, as the other ones. So, the other ones could be once a year, and this one could be twice a year. That's how that would be. Okay. This right here is just a big bearing, but it has an important name, and we talk about it a lot. And it's called a pillow block bearing, and it holds the shaft and the assembly to the frame of the wind turbine right here. This right over here that we're looking at, this thing, that's part of the frame of the turbine, and we call that the bed plate. It's kind of like a car. I don't know what that is over there. I've never seen one, and so this is an old thing. I think that's a heater, just a different kind of heater. The ones that I'd seen were in more of like a box, like up here.
Hey, John, on average, how many times a year is someone up in the nacelle of a wind turbine on a big industrial farm on average?
At least every 6 months. Now they do have well, you know, even though there might be people in there, they're not doing anything maybe but checking the oil, you know. So there are different maintenance cycles in different turbines on how often you have to do that, just depending. So a good example is like I have a BMW, you know, drive a BMW electric, but it has a little gas motor in there. And you have to check the gas to change the oil in that motor every 15,000 miles, which is weird because in most cars we do it about every 3 to 5. So, you know, it's going to depend on the maintenance cycle and the design of the turbine, the kind of oil they use, and how often you go up there to do some of the different tasks. But in general, they have semi-annual and annual maintenances regularly. So you're in there at least every 6 months. And then who knows if people are going up there and troubleshooting things. So what can happen is you could have a part of failure that's going bad, or you could have brushes. For example, you have brushes that run on the generator that make the connection points, and they wear down over time. And you don't always have like the original manufacturer brush, but you know, so you could get a brush that might be of lower quality, that doesn't last as long. And then it also could be a different time of year where maybe the generator is spinning much faster more often, and it's just causing more and more wear. So to be honest, every site has all different kinds of issues in all different levels and cycles that they have to go into. So you may have a turbine that's older, but the brushes wear out much faster than the newer turbines. So you have to go in every 3 months to change brushes on every single turbine. And that's just a pain in the butt or something, but that's part of the maintenance cycle on that site. Does that make sense?
It does. I'm trying to get a hold of just some standards in my mind of when I'm looking at the cost of operating a wind farm. You know, if it's highly skilled labor, you know, I work in developing countries, then we have to make sure that we have international experts coming in. But for some of the skills that you're pointing out here, we could hire locally. So it makes sense at least twice a year, probably more for folks that we could hire locally. And then the sort of, I guess, higher skilled troubleshooting folks, how often?
Well, there's usually at least a couple troubleshooters on standby all the time. The way to look at it is that you have, if you're only to get down to maybe 2 people, then those 2 people are going to be the troubleshooters and everything else. The only time they add more people is when the troubleshooters are too busy to do everything else. Does that make sense?
Yeah.
And that's going to depend on the size of the wind farm. So you could have a wind farm that has just 10 turbines on it, and only just need 1 person, and that 1 person can do it all, you know. And usually that's what happens. Or sometimes what happens is that wind farm contracts with a larger wind farm that has a large crew of wind techs of, say, like 25 techs, because they have maybe 100 plus wind turbines. And so those 25 wind techs are taking care of those, but they also have a contract to take care of maybe a couple of these, and they're just not there all the time, you know, so they just show up and bill them when they come and do their regular maintenance. So that's another way that some of the stuff happens, but usually you have to have at least one tech for every 10 turbines. And just depending on the size, I would say on most farms, you know, which are generally around 100 wind turbine size, you have about 20 people at the minimum. And you have the guys doing the regular maintenance, and you usually only have maybe a quarter of them that are troubleshooters, and they're doing all the high-end work. Then you have maybe 5 that handle more higher-end hydraulics or mechanical things, and then the rest of the people are doing more of the tedious, lower skilled work. And that's why I try to express to you guys, you know, some people quit the program and then they get a job and all they're doing is cleaning up after the other guys and changing oil and grease, you know. And so, yeah, they're a wind tech, but that's not what you went to school for. You're going to get into those jobs where you have some responsibility and you have a lot of you're not alienated from your labor. So, you know, that's kind of how the breakdown is. And it just depends on the farm and the turbine and even the company. Some companies don't like to hire troubleshooters because they don't do that kind of work. All they do is the general maintenance, low skilled stuff, and it gets contracted out that way. So I don't know if I answered your question there or not, but
yeah, that's a really good benchmark. 1 tech for every 10 industrial sized turbines about.
Yeah, you know, companies, they're going to want to make that lower if they can. But I think what happens is if you guys actually are able to keep these turbines running, you know, almost 100% of the time, and the turbines are getting better and better, you know, they're able to make good money. They're going to be able to pay you better and maintain larger crews and larger workforces. And that just make everything better. So I think it comes down to when the turbine is a piece of junk and it breaks all the time, and you have people who are not efficient at any of it, and it just gets too expensive. And you know, if we let the industry go in that direction and people don't take their job seriously, you know, we run into to a lower pay, really, industry. So what else? Okay, I have no idea what time it is.
12:30.
Thank you. Oh, we are there. We went over. Okay. Well, that means I was having a good time anyway. All right. So hopefully you found this exciting. We're not done. We'll just end here. But this worked pretty good. And hopefully you think this is interesting. So we'll look all over this turbine before we end today, or before we move on from this software. We'll look at everything and we'll come back to it. So this is the generator in the back, and then inside here is that other top box I was telling you about. And it's got a bunch of relays and control switches in there. So I'll just take this on out to the top just so you can see. There you go. You get up to the top, and that's one of the benefits of the job if you like seeing the view. So the other software I do have up running. I was going to show that to you if I got through this pretty quick, but we have a little bit more to look at, and then we got to finish up some hydraulics. So I wanted to get back to you guys touching on some of this stuff, if I can figure out how to get this thing to let me out. That's it.